Welcome to this example problem on heat conduction. In this scenario, we have a metal plate 4 millimeters thick with a thermal conductivity K of 95.5 watts per meter degree Celsius. This plate is exposed to vapor at 100 degrees Celsius on one side and cooling water at 25 degrees Celsius on the opposite side. We are given the heat transfer coefficients 14,500 watts per square meter degree Celsius for the vapor side and 2,250 watts per square meter degree Celsius for the water side. Our goal is to determine three key parameters. First, the rate of heat transfer. Second, the overall heat transfer coefficient. And finally, the temperature drop at each side of the heat transfer. Let's begin by listing the given parameters for our solution. The thickness of the metal plate, denoted as L, is 4 millimeters. The thermal conductivity of the plate material K is 95.5 watts per meter degree Celsius. The temperature of the hot fluid, vapor, is 100 degrees Celsius. The temperature of the cold fluid, the water, is 25 degrees. Finally, the heat transfer coefficients are given as HF for the vapor side, which is 14,500 watts per square meter degree Celsius, and HCF for the water side, which is 2,250 watts per square meter degree Celsius. Now let's calculate the rate of heat transfer per square meter. This is denoted as Q. We know that for a composite system, the rate of heat transfer is given by the overall temperature difference divided by the total thermal resistance. In this case, the overall temperature difference is the difference between the hot fluid temperature and the cold fluid temperature. The total thermal resistance, RTH, total, accounts for all resistances in series. Now, expanding on the total thermal resistance, it comprises three components: the convective resistance on the hot fluid side, the conductive resistance through the metal plate, and the convective resistance on the cold fluid side. Each of these resistances can be expressed in terms of the given parameters. Substituting the expressions for each thermal resistance, we get the equation for Q as the difference in temperature divided by the sum of the HHF plus L over K plus 1 over HCF. This formula directly incorporates the heat transfer coefficients and the plate's properties. So plugging in the values, we have 75 in the numerator, and in the denominator we have the values as given. And finally, once we perform the calculations, we find that the rate of heat transfer per square meter, Q, is given as 1.35 times 10 to the power 5 watts per square meter. This is the first answer representing the heat flowing through the plate per unit area. Next, let's determine the overall heat transfer coefficient U. We know that the rate of heat transfer through a composite system can be expressed as Q equals U times A times the overall temperature difference, where Q is the total heat transfer, A is the area. Since we calculated Q, which is Q over A, we can rearrange this equation to solve for U. Rearranging the formula, U equals Q divided by the overall temperature difference, substituting the value of Q we just calculated, multiplied by 10 to the power 5, and then dividing by the overall temperature difference. We find that the overall heat transfer coefficient U is equals to 1800 watts per square meter degree Celsius. This is our second answer. Finally, let's calculate the temperature drop at each side of the heat transfer. We know that the rate of heat transfer Q is constant throughout the system, and it is equal to 1.35 times 10 to the power 5 meters squared. Now for the temperature drop in the vapor film denoted by delta THF, we use the formula QHF equals delta THF divided by the convective resistance on the hot fluid side. Rearranging and substituting, we get the final value of the temperature drop as 9.31 degrees Celsius. Similarly, the temperature drop across a metal plate, we use Q12 equals delta 12 divided by the conductive resistance of the plate. Plugging in the numbers, we find the temperature drop in the metal to be 5.65 degrees Celsius. And finally, the temperature drop in the water film, we get this by having QCF equals delta CF divided by the convective resistance on the cold fluid side. So substituting the values and calculating, we get the temperature drop in the water film to be 60 degrees Celsius. So in summary, the temperature drop in the vapor film is 9.31 degrees Celsius. The temperature drop in the metal plate is 5.65 degrees Celsius. And the temperature drop in the water film is 60 degrees Celsius. These values represent the temperature difference across each individual resistance in the heat transfer path. To verify our calculations, the sum of these individual temperature drops should ideally equal the overall temperature difference. So adding 9.31, 5.65 and 60 degrees Celsius, we get approximately 74.96 degrees Celsius, which is very close to our initial temperature difference of 75 degrees. This confirms the consistency of our results. So to recap, we successfully determined the rate of heat transfer, the overall heat transfer coefficient, and the temperature drop across each component of the system. This comprehensive analysis provides a complete understanding of heat transfer through metal plate under given condition. So like, subscribe, and share.